Our speaker today is Professor César Huete. He received his 5-year degree in mechanical engineering at the University of Castilla-La Mancha in 2007. He earned his PhD at the same university in 2012. After his PhD completion, he moved to University of California, San Diego, to work with Professor Foreman Williams and Professor Antonio Sanchez on high-speed combustion, transonic mixing layers, and the ignition of reactive mixtures by shock impingement. So now as an associate professor at, I'm gonna try to pronounce this in Spanish, Universidad Carlos de Tres de Madrid. He's currently working. Yeah, it's close. I don't know. Yeah, he's currently working on topics related to high energy density physics, as there are the accretion shock influence on core collapse, the supernova, and the formation of ablation fronts by soft X-ray pulses in inertial confinement fusion. So I think now is the time to give the podium to Professor Huete, and please feel free to start your talk. Thank you.
Okay. Well, thank you, especially César, for making this possible, right? Because I mean, you are getting something that is quite important for us, gathering together the detonation community. Because maybe I'm speaking just about myself, but sometimes we just are looking into our work. We are so focused on our work, and this is the chance to get a broader view of the detonation. So thanks for that. I mean, this is, I mean, I really appreciate that.
Yeah, my pleasure.
Cool. The work I'm going to talk today is about the hydrodynamics. So I will focus on the dynamics of planar detonations in non-homogeneous media. I mean, I think that came from our latest publications in the Journal of Fluid Mechanics, where we were developing the theory to try to answer about how having non-uniform conditions upstream may affect the propagation of a detonation wave, a planar detonation wave. And this work is actually part of the PhD of Alberto Quadra, which I think he's now in the room, and also Marcos Vera, who is a full professor here at the university, that he'll helping us in the thermochemistry part. Well, this is the outline. The thing is, I will start with some fundamentals. I'm sure that all of you know that, but I think it's worth to stay all on the same page and to try to unify the notation I will use throughout the talk. So that's why you will see that some part of the introduction, you know that for sure. We'll start with the problem, the initial value problem, where it means that what happens if the planar detonation is initially distorted, and then we may be ready once we have shown the mathematical formalism to include perturbations upstream. We start with mono-chromatic perturbations, then we add the full spectrum. We do the corresponding integral, weighted integral to move from here to that. And then we try to answer the final question, which is the question at the beginning, how these may affect the detonation propagation velocity. Well, the introduction. For sure, you all know that the detonation, if we look at the CZND configuration, if temperature behind the shock is sufficiently high, this is the Neumann conditions, then you trigger the reaction, and at some point the field is depleted, and then the reaction is over, and you get the final downstream condition, right? So you move from upstream to downstream conditions, and you can see here. If we look at that into the well-known Rankine-Hugoniot curve, it's quite simple to do what is going on. Is that you start with the initial condition for density and pressure, or specific volume in that axis. And then the blue curve corresponds to all possible post-shock solutions for inert shocks, right? So if we take the Dobitz-Neumann-Doring configurations, we move from the green point to the blue point, and then we move downwards to the green to the orange points, with the orange curve correspond to the Rankine-Hugoniot for an exothermic reaction, reactive wave, that is detonation. So far, it's quite simple. The thing is that we have to be careful about, because there is no left-hand scale written here. I mean, from green to blue, there is like a of the order of the mean free path, but from blue to orange, there is actually a microscopic, or sometimes even larger length scale. So careful with that. Well, the point is that the Chapman-Huete conditions are the tricky condition for detonations, but are also those that really happens in nature. There is for sure, if I have a higher heat release, the orange curve moves upwards, and there is a maximum heat release or a minimum propagation velocity that is called the Chapman-Huete condition, right? Well, this condition is singular because this condition is given by the sonic condition downstream. Okay, what it means is that if you have here, if you trigger and you are expanding, right? You see that from blue to orange, we have lower pressure, we are moving sorry, this is the other way around, to higher specific volume, lower density. So we are expanding, we are accelerating, we are having a rocket type effect pushing forward the shock wave, right? But there is this critical condition is the maximum expansion we can get. Because if you look at the characteristics, there is from that point forth, I don't know what's going on. I cannot, this is acoustically decoupled. We cannot affect outside because my region of influence is bounded by the sonic condition. So it's the maximum expansion I can get for a given heat of release. Well, if we look at that, the thing is that there is a parameter that is very important in the perturbation analysis, and that's why I did the introduction, that for sure all of you know that, is this gamma factor, which is the slope of the Rayleigh-Michelson line, which is that one, given by the conservation of mass and momentum only. Here, it does not change with heat release, that's why it does not change here in the graph, with respect to the Rankine-Hugoniot curve. At the point we are working on Chapman-Huete conditions, this tends to unity, and you will see that effect later and in the perturbation equation. So bear that in mind, that this gamma function, when the curve becomes tangent, becomes unity. And this is given the formal expression of this value. Well, this tangent, this sonic condition is singular. I mean, you can find that in many problems in detonation. For instance, something that is not related with the problem I'm going to talk today is the so-called Feldovitz-Taylor detonation, right? Which is the similar solution of a constant moving detonation at Chapman-Huete. What happens is here, because of that, the slope becomes infinite. Here, there's another simulations. At a given point, it reaches that condition. And here we see that the slope of the variables become infinite. And this is given by this singular condition. In reality, we have to be careful about that because here, where we are looking is to one-dimensional steady solutions. In reality, there are unsteady effects. I mean, we may have unsteady terms not included in the conservation equations, in the steady one-dimensional conservation effects equations that can't, that of course play a role when we are here. So why I'm saying so, because if you look at that, the perturbation of the detonation velocity, which is the slope of this equation of this line, can, in principle, it cannot move to this direction because the curve detached, right? So that's why I'm telling you that we have to be careful when looking at that, because this is good for average properties. But when looking into the perturbation analysis, we have to be careful because in perturbation analysis, we are restricted, highly restricted by this tangent condition here. And there are different approaches. And for instance, this does the coupling by looking at the solid surface when it is not the same at the end of the reaction zone that happens here in steady two-dimensional detonations. And that's what I said before. That's the word of Mate. They say the same thing, that in different words. You can look at the paper. But the thing is that in average conditions, they work pretty well. But you have to look at the perturbations. You have some criticality by this sonic condition. Well, the paper we are going to study in detail in this talk deals with perturbations in density and heat release upstream. So what's in fact what we have is, instead of the blue curve, we have like a here we are disturbing, we allow perturbations. So this is not a single curve, but actually a few of them. And afterwards, when looking into the spectrum, what we have is a spectrum for the possibility of having this perturbation in density and this perturbation in density in one direction or the other. And the same would apply for perturbation in heat release. We have like a spectrum too. And the shock also reacts with the perturbation in the propagation speed. So we have the slope of this Rayleigh-Nicholson line is also affected by these perturbations. In linear theory, those perturbations are of the same order. So the perturbations here and the amplitude of the perturbations downstream is of the same order of the perturbations upstream, right? If you include nonlinear terms, that things have to be rethought carefully. So let's look at the initial value problem. So the thing is that, think about instead of having a planar detonation, eventually it gets distorted, right? And still we think about the fast reaction limit, that everything is burned right behind the shock. So we don't see an inner structure. And I will talk to the inner structure at the end of the talk to see, actually to get some feedback about some thoughts. Well, it's quite simple to see that if this part of the detonation is accelerating and this is decelerating, right? You have a higher Mach number, local higher Mach number associated to this part. So here we are compressing higher, and here we are compressing less. So we have a different velocity here is affected by different delta O, delta U, okay? But there is another thing which is even more important, actually coupled with that, is that because of here, locally, we have an oblique detonation. So we are generating a transverse velocity. We are generating a transverse velocity flow downstream that in principle, it didn't exist upstream. So if you look at the final picture, what we have is like we have this tangent velocity generated across the detonation. And if you see what is going on is that, okay, I had a distorted detonation, okay? But because of the tangential velocity, I'm pushing mass here, increasing pressure. I'm increasing pressure here, and I'm lowering the pressure in this region. So the gas dynamics behind the detonations tends to reduce this distortion and actually plays the opposite role. So it wants to move, the effect is wants to move the detonation into the planar shape in both directions, right? But the thing is that it's not that simple because this is a dynamic problem. And what we find at the very end is that if you look at the detonation amplitude, it actually oscillates because there is a characteristic time here given by the speed of sound downstream and the characteristic wavelength. And this competition of these two effects, it takes its time. So it's like here I'm winning and losing and so and so and so and so. Okay, so this is essentially what happens with the gas dynamics behind the shock or the detonation actually, if we neglect the effect in the inner structure. So let's do the perturbation analysis properly. So, well, here they are not quite deductive. So the perturbation is like, let's assume I have a perturbation that it's small, and this is measured with the pressure given by temperature, right? So, and this is an order of unity value. This pressure is order of unity. So the factor epsilon is what accounts for the amplitude of the perturbations. in linear theory, here, the perturbation is factored out, and at the end, it doesn't play any role. But when you look into non-linear terms, this effect is important and plays a role, because you have to evaluate the weights of this term in comparison to other effects, right? So the same for pressure. We are looking into how pressure deviates from uniform conditions, the same for density, velocity, longitudinal and transverse velocities. And the initial value problem is saying, okay, what happens is a given time and provides initial perturbations. Let's see how the detonation evolves due to the gas dynamics counter effects that play right behind the detonation. Those I've shown to you before. So to do that, the only thing we have to do, only is not that trivial, which if you want to look at the transient, is to couple the Euler equations, because once the combustion is over, there is actually at this speed diffusion, viscosity does not play any role at the beginning. Afterwards, of course, it will play a role, but behind the detonation, it does not. It's very high Reynolds. And you have to couple that with the boundary conditions at the detonation. And this is the linearized Rankine-Hugoniot equations that takes into account the tangential velocity conservation of energy, and this is actually conservation of mass, momentum, and energy coupled. Anyhow, what happens in the Chapman you get for the linear perturbation problem? If you remember, I recall that now, gamma tends to unity in the Chapman you get. So look at what happened here. This factor tends to 0, and actually that's what happens. This is not 0. This is an order of unity term determined by the tangential velocity conservation. We have something that tends to 0 here. So what happens is pressure grows unbounded if you look at exactly a Chapman you get conditions. So that's why you cannot look, tends to infinity when gamma tends to unity. That's why you cannot place exactly Chapman you get conditions in the fast reaction limit. To solve this, there are strategies that I showed this on the detonation shock theory. You can decouple the sonic locus with the reaction region, and you can work it out. But if you look at the fast reaction limit, there is no way to go away from that. There is no form to do it. Fortunately, it happens in a very, very weak manner. I mean, you can move to weaker and weaker overdrives, and it's not that bad, okay? So actually, the Euler equations, if just the sum with equation for pressure, I told you before, the epsilon, the amplitude, does not play any role in linear theory, and it has to be solved with 2 initial conditions and 2 boundary conditions. One boundary condition is given at the detonation, which the equation I showed to you before, those one that you cannot see anything right now. And the other is given by the pushing of our detonation. If we assume that this is isolated, it means that there is no wave reaching the detonation from behind, okay? And this is a very justified assumption when we are dealing with weak overdrive detonations. And I will tell you now in a minute. And the other is the 2 initial conditions. For the asymptotic problem, for the long time regime, they don't matter at all. They will reach the asymptotic value in linear theory. It does not depend on the initial conditions. But if you want to look at the transient, you have to properly take them into account. So this is in the burn gas reference frame. That's what we have. I mean, let me show you first the laboratory reference frames. You have a detonation in the spatio-temporal, and particles do not move until they reach the front, and the detonation push them moving, follow with the detonation, right? It's like an oblique detonation in the xt space, like an xy, like an oblique. It looks like a steady oblique detonation. But here, if we want to look at, if we want to stay in the burn gas reference frame, we are rotating this in such a way that this is straight, and this is like that. Okay. So what we see is that in the Barnard reference frame, the fluid particles are moving to us, and then they are put at rest right behind. The important thing about the Chapman-Huguet is that these characteristics, so you can split into two different characteristics, those sound waves moving backwards, sound waves moving upwards, close to Chapman-Huguet, these becomes parallel. Okay, the C-mass characteristics becomes parallel. But the thing is, I mean, the most important thing here is that even if we cannot look into the purely Chapman-Huguet conditions because they become singular, as we have shown before, the thing is that they don't matter at all. I need a piston if I need some overdrive. I need something to keep pressure upper than found in overdriven in Chapman-Huguet detonations. So I need a piston for sure. But the effect of the piston is negligible because in weak overdrives, because of the Doppler effect. And let me show that because I think it's interesting. Think about what I told you before. You have a detonation that is given with a given frequency, is oscillating in time, assuming that this is stable. Okay. If I include the piston, there are some reverberation, some reflected wave coming back and forth, back and forth, back and forth. But because of these are almost parallel, this frequency is much more slower. Frequency smaller, much larger wavelength, that in our time reference frame, the role that it plays can be neglected. So we can use this isolated assumption for weakly overdrives. I think that I will not go through details to that, but the point is that if you know the Laplace transform for the detonation pressure, or here this is the detonation amplitude or the detonation pressure, they are, you know one, you know the other, you can do the proper integration and calculate the transient evolution. Okay, and this is, for instance, what you find for the detonation. This is the detonation. Initially is unity because it is used to non-dimensionalize the problem, and this is pressure. When you see that this is the history of the pressure at the detonation, and the other is the pressure in the whole spatial domain downstream. What you see here is like you see sound waves moving following the detonation, and they are right. But if you place yourself at the detonation, they are escaping. Okay, this is just it's somewhat tricky trying to cheat us, but this is not. It is not. They are not catching up the detonation because we have assumed the detonation travel isolated. It's just a visual effect associated to these pressure perturbations, and actually associated to the dynamics of the detonations, that they are moving like that to generate different tangential velocity patterns. What you are doing is you are building vortices downstream, so that you can look at the vorticity footprints behind the detonation too. Well, now let's look at the problem, and we'll see that the mathematical formalism is quite similar. So I think we are now ready to use it to include not the initial value problem, but to include a continuous exactment at the detonation front. So this is the problem configuration, the same as before, but I'm now continuously give same detonation that here density is higher, here is lower, and so on, so on, so. So the thing is that now we are opening many variables. For instance, other perturbations, maybe perturbations in pressure, density, velocity, field mass fraction that associated to enthalpy of formations. So you have many of them. Now you have to model not only the detonation, but you have to model why your flow as upstream is not uniform. So you need to set your problem in a proper configuration. And you say, for instance, if you are looking what it's usually done for shock waves in turbulent boundary layers, you can apply Markovian hypothesis to correlate density and velocity perturbations. If you are doing with some turbulence mixing, depending on conditions, they are correlated in a different way. So the thing is that now you have like two problems that you want to put together. One is the detonation, and the other is the what is giving you the perturbations upstream, okay? So the thing is that now we have the length scale, but we also had the detonation length scale associated to the thickness, right? So for the thin detonation to be okay, you have to be in the limit that this is much smaller than the perturbations upstream, okay? Because we have two lengths, two independent lengths. There are different problems at all. I mean, this perturbation does anything to do with the detonation thickness. So that's why you have to say something from the external model to say, okay, which one is the dominant one? Well, we are lucky because detonations are typically formed by strong shock waves. They are led by strong shock waves. So if you go to the Rankine-Hugoniot equations, the same as shown to you before, okay, we see here that we have this term that this converges to order of unity value for a strong shock, the upstream, the denominator, but in the denominator we have the Mach number. And for pressure, we have the same thing. This is an order of unity in the strong shock, and this is something that the Mach number grows unbounded with the shock strength. I mean, this is the variable we are looking at. So we can actually neglect the velocity and pressure perturbations if the amplitude are of the same order at density, because what dominates in the strong shock limit is density. I mean, the question for that is quite simple. If you look at the mass compression ratio for a shock wave as a function of the Mach number, you see that it does something like that, right? For a shock wave, it gives you that. For a planar detonation, for a detonation in the term you get, is giving you, sorry, without it, okay? You have a lower density downstream because of the expansion of the reacting flow. So what happens is that no matter how how strong is the shock, density is always finite. So if you want to put some perturbations upstream, I will see always these perturbations downstream. But this is not what happened for pressure and density. For velocity. Velocity of the shock grows with the Mach number for sure, and pressure grows with the Mach number squared. So at some point, if I have perturbation of velocity and pressure, if I'm sufficiently strong with the shock, this perturbation will become negligible at the end of the day. But this is not what happened for density. That's why density is so important. And the same happened for the heat release in the energy equation. So that's what justifies using, even if you have a mixing effect where density, pressure, velocity, and they are not in equilibrium because you have this mixing process occurring ahead of the detonation. You can forget about the other variables. You have to focus on the density upstream because this is what dominates the detonation behavior downstream. So this is the case we want to look at, is that what happens if we have an incomplete mixing upstream. So we have to model how variations in the fuel mass fractions are related to the variables that actually affect the conservation equations. And I think this is the most important part to understand the role of these perturbations. Think, for instance, that you have this non-uniform pattern upstream, and you have some points that you have a positive fuel mass fraction, and you have a negative fuel mass fraction perturbation with respect to the average mixture. So think about that if you are looking into a very light fuel, this positive fuel mass fraction will give you less density. If you are on the right-hand side of the peak of the heat release, these higher density, these higher heat perturbations will give you a lower heat release. And this is a counter effect that produces destructive interference. Less density is less oppositions. I want to move forward. Lower potential, lower expansion, lower push by the expansion. It want me to move less. I mean, in talking perturbations. So they compensate each other. I mean, compensate. We have to look at the how big they are. But qualitatively speaking, they compensate. So they render a destructive interference. And the same occurs here with the opposite signs. Now, if we have less density but a higher potential, these two effects go on the same directions. Less density, the detonation wants to move faster because there is less opposition. Higher potential, higher combustion heat, it wants to move also in that direction. So, for instance, what can we do to look at that? Is to look at different curves for density as a function of the fuel mass fractions relative to the stoichiometric mixture, and the same for, okay? So looking at that, for instance, if we look at this curve for methane, we see that this density is practically is linear here, it's almost linear with the fuel mass fraction, and we have like a positive values of the fuel mass fraction. Perturbation will give me lower density because the slope is negative. And here we have the other curve, which is the potential heat of combustion. And we have, if we are close to the stoichiometric condition, we have the maximum, not exactly at that, but roughly speaking at that. We may have constructive interference on this side and destructive interference on the right-hand side. And we can get the opposite thing if this slope is reverted for heavier fuels. And this, actually, I didn't comment that, sorry. Yes, no, it was here. We have to perturb the variation of density is given by the average plus the variation of the fuel mass fraction plus this slope. This slope is how density changes with the fuel mass fraction. And we have the same thing here. The variation of heat release is the average value, and we include the variation of the fuel mass fraction, and H is the variation of heat with respect to the fuel mass fraction. And we see these blue and orange regions correspond to positive and negative interferences, as I told you before. So how can we solve this problem when we have a continuous perturbation field upstream? So this is the same as before. I mean, this is the same equations, but we have to include something that this is the upstream excitation term. And this is what we do if we look at directly to the asymptotic theory, when you assume that we can apply actually normal modes analysis. And here we have our amplitudes relative to the, if we are in heavy or lighter fuels, and in the left-hand side or right-hand side of the peak in the heat of combustion. So the good thing about the perturbation analysis and the Laplace transform is that we can get exactly the pressure as a function of time. So this is an analytical expression. And we find different solutions depending on the oscillation frequency. If the detonation oscillates with a low frequency, low is that in terms of this is how this kappa x kappa y is actually lambda y lambda x, right? This is of course the wave number and the wavelength. It generates pressure that decays in time. If the pressure is sufficiently high, it crosses this value unity in this critical frequency. I mean, it's a scale with that critical frequency. That's why the key thing is unity. You have constant oscillation of pressure following the detonation, the same movie I showed you before. And if the frequency is sufficiently high, the vector defining the pressure field pointing backwards, and you have that all your downstream flow will be filled with sound waves. Another thing is that we have shown in our work is that you can find solutions where there is no pressure perturbation downstream, and they are given by these counter effects between density and heat release. depending on the correlation of H and W, depending on the correlation, the slope of the hydrolysis and density curves, you can get conditions. This red curve correspond to the condition where there is no pressure perturbations at all. It's like the detonation is oscillating, but it does not generate pressure perturbation at all. It's in equilibrium. It's like it's moving at the frequency it has to move, and there is nothing that generates a pressure disturbances downstream. But you can also get conditions where there is no ripple. It's like this destructive interference is making you a no ripple, but it's giving you a longitudinal. It's like it's moving like back and forth with respect to the planar position, right? But it does not generate a ripple. So that's a very nice thing we solved for. We can also compute, and this is important to calculate the turbulent spectrum. We can also compute what is the value of the for instance, the velocity, rotational contribution of velocity as a function of the angle, right? So depending on the angle, which is essentially depending on how lambda x over lambda y is, you get a different value of the density of the velocity perturbation downstream. So here is plotted in a polar plot to make it. I think it looks nicer, but at the end of the day, what you have is if you look at this angle, right, and you have like depending on the angle, you have a different amplitude for these perturbations. You can do that for velocity, density, and pressure, or whatever. Now, these amplitudes were given in the long time regime. Okay, applying normal modes analysis. What I showed you before in the equations, applying normal modes analysis. You cannot use the normal modes analysis to calculate the transient evolution. And we have to be really careful about that, because if you are close to the critical conditions, close to Z equals unity, then it takes a life to get the final asymptotic. This is the asymptotic expression. This is what is giving you the normal modes analysis, and this is what is actually happening at the detonations if you start the initial problem from the beginning of the time. So it might be unrealistic to consider this amplitude in the long-term regime, because actually it takes forever to achieve that. And if, for instance, if you move to a higher frequency, the asymptotic theory and the transient evolution is actually the same. I mean, 3 oscillations and they are actually the same, effectively the same. So an open question that I have no answer is that what happens if we include the nonlinear perturbation, something that can be done with a numerical code. And my question is related to the one of the hypotheses I assume here. I'm assuming that the detonation is stable, okay? It's like a base flow, no perturbation. The initial value problem is giving you a constant in the long time regime. But this is close to Chaman you get for mostly in practical cases, the activation energy high, temperature is that sensitivity in the exponential of the reaction rate is giving you that stable cellular pattern that all of you know. So I wonder if it is possible, I have no answer for that, to generate like a passive control of that in the way that you are forcing the detonation to do what you want to do. It's like, I have a very low density here, very higher density here, and this nonlinear is governing the detonation rather instead of the self-induced detonation of the detonation wave, self-induced oscillations. So it has to be, it will depend on the amplitude. So linear theory cannot be applied, and it would depend on the frequency. And there might be likely a frequency from which you can do that. Well, let's look now at the isotropic spectrum, which is actually what happens when you have a real mixture. To do that, we have to move from the single mode problem, single frequency, to a spectrum. What we do is to assume that we have an isotropic spectrum upstream. This is pretty similar. I mean, there had been few works on that. In shock waves, the original works were done by Ribner in the 50s. In detonations, with the same assumption as here, by including the fast reaction limit, they were done by Jackson in the 90s. So I mean, the theory here about the turbulence generated by the detonation in this condition is the same as those in those papers. What I'm going to do is to use these effects, which is actually pretty known, to calculate how that affect to the detonation velocity. And this is something that I haven't seen in literature with this formulation. Okay, the first thing we need to do is a probability spectrum, right? So you know that I told you that, for instance, velocity depends on the angle of the perturbation upstream. Actually, depends on the, right? Depends on how these two guys are related. But we have to include a probability density distribution because some of them may happen very likely, and some of them are less likely to happen. If we are in an isotropic spectrum, we have to add another spectrum to weight these values. So when looking into mixtures, this is like a passive scalar, you see that if you look at the Filmer fraction, temperature, and pressure, you see that they mostly look the same for isotropic spectrum. So that makes you, that suggests that you can use the same type of spectrum used for turbulence but apply for the Filmer fraction. And it makes sense because if they are generated by the same phenomena, they has to be correlated for sure. So we can calculate the isotropic spectrum. We can, for instance, calculate the acoustic contribution, the rotational contribution, and in 2 dimensions, 3 dimensions. I mean, for the linear theory, there is no difference at all. I mean, it's just, instead of doing the average in this, you have to do the average in that. But there is no mathematical, there is no computational penalization that you will find for sure. You have to do the code, actually a numerical code accounting for everything. It's not, it for sure is not that. It's much more complicated. And you can also split into, as I said, 2D, 3D, rotational and acoustic, or longitudinal and transverse velocities. The thing that this is important here is that we are plotting different correlations. What happens when the black lines, when this density dominates the perturbations upstream, the green line is what happens with heat release dominates the perturbations when they are the same, but we are the same, but with the opposite sign. So this is like the four, they are not limiting cases because you can move that, you have, but distinguish, this is the distinguished cases. I'm not going to explain all of them for sure. I mean, this is going to get a roughly impression about what you can do. The thing is that that the one that behaves quite differently is that dominated by heat perturbations, where amplitude is usually much smaller. And the other thing that has to be here noticed is that acoustic perturbations, this, sorry, I didn't say what is the axis. This is the overdrive. This is actually like a shock, and this is like a Chapman-Huguet detonation. For Chapman-Huguet conditions, the acoustic contribution goes unbounded. And this is the gamma tends to unity thing I told you at the beginning of the talk. We can also look at to the formula, the spectrum downstream, but here we have to be careful. But now we are comparing with a length, which is the upstream wavelength. Very high values of the wavelength correspond to very small values of the corresponding length associated to the perturbations upstream. So we have to be careful because when looking into the spectrum, here we have like the higher voltage, higher patches of perturbations, the smaller. At some point, they will become comparable to the detonation thickness. So we have to, this limit has to be determined by the corresponding condition of what is the turbulent spectrum upstream, the characteristic length upstream, and what is the characteristic length in the characteristic time in the chemical process. So they are two independent variables, and then you have to look at that to see if this spectrum may apply or not. And finally, Once we have moved from the initial perturbations, constant oscillations, and spectrums, we are ready to tackle the problem that how these perturbations downstreams affect the shock propagation properties. And we started this work because there were a few works before on shock waves using a model similar to that I'm going to show you now. And the thing is that for shock waves, they find that if you generate turbulence downstream, this turbulence modified the average values of the Rankine-Hugoniot equations. And as a consequence, the velocity of the wave, let's say a shock or a detonation, is affected by this generation of turbulence. For example, what I want to say is that you remember the curve I showed you before. This is the Rankine-Hugoniot curve. There are second order corrections to the specific volume of density or pressure associated to the turbulent averages. And that's what we want to look at. And we find, I mean, the point is that we draw this arrow in these directions because this is what actually happens. If you look at on a shock wave, forget about the correlations between the fuel, the heat of combustion and density. If you look at a shock wave, what you find is that pressure is lower and density is lower when doing these turbulent averages. So this is really similar to what you find in a detonation in the qualitative picture. You remember we had the blue point and we moved to the orange point exactly in the same direction. So qualitatively speaking, what we have is like for a shock wave, we have like an exothermicity taking place. It's not that, but in this plane, it looks like that. So we thought that, okay, if turbulence makes a shock move faster, maybe it's exactly the same for a detonation. Instead of that, we have to include also the heat release, but there is this effect that may take the same role. So we do the turbulent averages. So I refer to the paper for details. I think I've already spent too much time, I mean, in that, and maybe it's not needed to do the rough discussion. Okay, so the thing is that we have the mass compression ratio, the pressure amplification factor, and the velocity correction, and we have second order corrections to these values. We have to do the corresponding averages of the turbulent field. It's not straightforward. I mean, you have to be careful that some of the function defining the averages have to be how to say that. If you the average, for instance, of velocity longitudinal, a velocity transfer is giving you a null, because this go with the cosine, this go with the sine, so there is no average, and you have to be careful with that. You have to be careful with that also with the space and temporal averages, because sometimes you get no, when they are orthogonal, they do not provide an average value. This is the sentence. What really matters is that how density is affected by these turbulent averages, by these continuous perturbations behind the detonation front. So what happens is that detonation density is lowered. This is negative. The correction is negative. Pressure is lowered. Velocity is higher, and this is positive. Also, the Mach number behind. So. And then you have the four curves correspond to when density dominates, when heat release dominates, and when there are positive or negative correlated. Okay, so the thing is that if density is lowered and pressure is lower and the same and velocity is higher, what happens with the detonation propagation speed? So this sketch is quite important, because here we see that if this is true, I mean, negative in density moving like that, negative in pressure moving like that, so positive in a specific volume. So what we have is that the effect of the turbulent averages is similar to that found in exothermic reactive shocks like detonations. So we are expecting to get a correction to the velocity that goes in the positive directions. We expect to get a faster propagation speed. And for instance, this is I think that Xiaosheng will talk about that in the next session, but they were doing these numerical simulations on this over condition in the Chapman-Huguet, and they find that the average velocity is usually higher. I mean, at some point, you can stop me if I say something wrong. They are allowed to use non-linear perturbation. Actually, they can concentrate quite high the energy of the perturbations upstream. Here, what we can compare is the values when this gamma, which is the concentration parameter, is close to unity, which is like the almost linear perturbations the linear perturbation we are looking at. It's like perturbations are highly diluted into the gas. So for us, this slope is what we use to perturb our problem. Of course, with the code, they can go much further in the analysis and look into the nonlinear problem. This is important because what I told you before is that density is lower, pressure is lower, velocity is higher. This is the same thing that happens in an exothermic reaction. This is the expansion of the flow. The thing is that if you want to close your problem, you have to say, okay, you are telling me that pressure, for instance, look at the pressure that it really is, or look at the velocity is really simple to understand. You are telling me that in average, velocity of the flow is higher. But think about the case that I have a moving piston, and this is me, the piston, which is controlling the flow particles behind the shock wave. Think about the shock, that this is easier. So I'm telling you that this average in the velocity, they cannot, they have to, the average in the velocity has to be zero, because this is me with the piston telling the fluid particle which velocity they have to move. So this is like a contradiction, because we are saying, okay, the Rankine-Hugoniot is telling me that velocity is higher, but is the piston which is telling the velocity, the fluid particles, how to move? Well, what breaks this paradox is that we haven't said anything about the velocity propagation speed. Actually, what we are saying, if we are moving at a constant speed, with no perturbation, then delta U must be positive. But this is moving in that reference frame. I can do the opposite analysis. What would be the correction to the velocity so that these perturbations in velocity is zero according to the piston that governs the fluid particles behind? And you can do that for pressure too. You can say, no, detonation, you are not governing the pressure. This is me behind what is telling the fluid particle which pressure they must show. But this is exactly the same thing. There is a free variable here, which is the shock propagation velocity that closes the system. And here, what we choose the condition is that the Mach number for Chapman-Huguet conditions, the one that better applies is that Mach number perturbations must be zero. So that's what we have here in average. So this is telling me, okay, what has to be the correction to the propagation speed so that, taking into account that Rankine-Hugoniot equations are modified, the Mach number behind is not modified. The thing is that regardless the condition that you use to close your system, either you know the velocity downstream, you know the pressure, and you don't allow perturbation in the Mach number, either of them doesn't matter. They don't change the qualitative picture. Okay, so that's the results. What we find is that except for the green lines, when perturbation of hydrolysis dominates, most of the cases show a positive deviation of velocity, even if we are looking into weaker overdrive or strong overdrives. And here we do the same thing. I think I didn't show that. I changed this is not the caption for this figure, sure, but this is for a different heat release. So, but the picture is roughly the same. You can also look at what happens with the adiabatic index. If we look at that, we see that in most of the cases, when there is heat release, there is like a positive variation. This is always positive, the velocity correction, but it is higher so long as the adiabatic index goes higher and higher. But here, when density dominates, we have the opposite trend. And we have to look at, we have to talk to Xiaoshen, because in that case, the theory aligns well when density perturbations dominate. But here, maybe there is an over prediction when heat release take a dominant role. So, I mean, we have to do the proper comparison, the quantitative comparison. But to do that, it's like we have to talk about the numerical and theoretical experiment with the same parameters, because there are too many free parameters to do a real quantitative comparison, which it has to be done later. And we can also look at heat release. And again, we see that in most of the cases, you get a positive. Here is always positive. But when you look at the strong overdrive, you may find negative deviation of the shock speed. But look at the numbers here. What theory says is that the speed of the detonations is corrected in a negative way. I mean, it moves slower manner, but look at the numbers. I mean, I'm sure that the error bars associated to the model are higher than these values predicted by theory. So we have to look at that, and I take it carefully, because there might be, this is not an order of unity correction. So to conclude, we have shown that thin detonation limit allows you to write analytical expressions. It can be very good to compare the evolution, the transient evolution of the detonation front. We can apply the work for turbulence perturbations upstream. We can include this effect of the second order perturbations into the analysis to calculate how this turbulence generated or amplified, depending on condition upstream, affect the propagation of the velocity, which is the most important contribution of this work. And what we find that in most of the cases of interest, because of this condition, the turbulent extra expansion generated by turbulence, the detonation is seen to propagate faster, okay?
My question is about like this fluctuation or this perturbance you introduced in energy release, or so basically like if you introduce the perturbation in the composition, so that change the density and also changes the equivalence ratio, so that the energy release is changed. So in that case, then you actually make the mixture either, for example, if the average case is the stoichiometric case, then you actually make the mixture linear or richer by introducing these fluctuations. So I don't know, like eventually when you compare the propagation speed of a detonation, would you compare that with the CJ velocity for the average stoichiometric case, or you compare that to somehow the average of the perturbed or the mixture with the fluctuations in equivalence ratio? I just wonder. Yeah.
We compare with the case that there is a perfect mixing with no fluctuation at all. Like what would happen with if you just plug the numbers about the heat of release and you calculate the detonation, somehow you get conditions. So
okay.
The comparison is the perturbation theory with no perturbation. I don't know.
Okay, yeah, I see what you mean. So in that case, actually, I think that's this correction you show that the propagation speed might be greater than CJ. That's even more significant than what we saw in our system is because actually in your case, then this what is not perturbed or this mixture, for example, it is a stoichiometry. I think that somehow is close to the upper limit of the CJ velocity that can go in this homogeneous system, right? Either you make it very rich or very lean, that actually reduces the homogeneous CJ velocity, right? But even in that case, even you use
Yes.
that CJ velocity as a reference, you still see a an increase or like a correction to the positive side for some cases. I believe it's when you see this strong density fluctuations, you see a positive effect on the propagation velocity. So yeah, I just think that's kind of interesting. And as you said, like it's not exactly the same system as what we studied, but it's I think it's good to think about it. What's the link between this?
Yes. Actually, if I move to this slide,
Yeah.
this is the slope of the sorry, I had to go to
Right.
sorry. This is the slope of the heat release curve, and this is the slope of the density curve for a given fuel, right?
Mm-hmm.
What we see is that regardless if we are looking into would be the lean side, positive slope, the rich side, negative slope, and this is for they correspond to negative. So light fuels or heavy fuels, regardless that, we always see the same qualitative corrections. That density is lower. But this value would depend on the condition you choose in your mixture. If your mixture is giving you this value, well, this would be the corrections. If you have a heavy, rich, you would get that in that region. So it depends on the condition you have upstream. But they are always measured with the corresponding uniform conditions, regardless if you are looking into the peak stoichiometric condition or others.
Okay.
Of course, I mean, this is theoretical. I mean, you cannot move away from because there are limited flammability that they are not taking here into account. So maybe, I mean, this is not appropriate to look very far away in this region, because you will find that at some point there is no reaction at all.
Right. Okay. Yeah, that's one of my questions, and maybe I would like others to ask first. I think Professor Charles Kianda turned on his video. Are you gonna? Yeah, please go ahead.
I've not looked at these problems in a while, but I just want to make sure I'm understanding right what you're doing. I think just there's a lot to unpack here. So maybe if you can just go back where you presented the perturbation equations, the perturbation dynamics there in the first third of your talk there. So you're looking at the perturbation dynamics in the flow downstream of the burnt surface of the detonation, with the detonation sonic locus as a boundary condition, right? Is that?
Or here, here is roughly the same.
Yeah, this is what I'm understanding, right? So you're assuming a completely thin detonation with no reactive structure to it. And,
yes.
And it acts as a boundary condition on the perturbation dynamics downstream of the detonation. So
yes.
Are you able to reconcile this work with
yes.
But the detonation itself is intrinsically stable or unstable to certain perturbations, right? So
actually, and that depends on the structure too. Yes.
Yes. So I'm just wondering if, I mean, I find the work you've done. I mean, I find the underneath, like I'd love to sit for a day and have beers and coffee, because I'm wondering if the underlying, the downstream dynamics may influence the sonic locus, and then you actually, because that's the question we keep having, right? Is whether the sonic locus is even, however you want to call it, the sonic locus, the limiting characteristics or whatnot. if you can even treat that as a
Yes.
as a hermetic boundary between the downstream flow and the detonation structure in multidimensional problems. So I'm just wondering if you can, because then your assumption, like in the back of my head, when I'm always thinking, I'm sorry, this is turning into a long comment there, but in the back of my head, what I keep thinking is that by treating instantaneous reactions completely thin, it's like you're doing a square detonation wave with zero activation energy, so that it has zero induction time. Is that the underlying?
The square.
Oh no! We lose you again.
Actually, can you listen to me?
I can hear you. You cut for a little bit.
Can you? Yeah. The square wave model actually is like the opposite, and this is actually unstable, unconditionally unstable. This is like the other case. Yeah, we are assuming that this is stable, and we know that it might not be true. Actually,
we know it's generally not true.
Generally not true. I mean, the work by here, the work by Short, and there are normal modes analysis, including the reaction rate, and they show that you have to be in strong overdrives to expect, and I say expect to get some kind of stabilization. So what we want to do
for the one-dimensional case, right? For the one-dimensional problem, or for the two-dimensional problem, you can get unconditionally unstable even in overdrive. Right? Am I remembering this wrong? We couldn't hear Mark Short's comment. Unfortunately, I wish he could comment on this. He'd probably be the one to correct me here.
Yes. It is a privileged condition to answer this question. And that's why I wanted to know if there is the possibility that the open question I saw in the middle of the talk about if we can somewhat force the detonation to do what we want it to do with by accounting upstream perturbations, nonlinear upstream perturbations.
Sorry, say that again.
It's like so if we were able to just like an academic problem, I don't know if it could be practiced or not, probably yes. If we are able to force the detonation to behave in the way we want to do, it's like upstream perturbations is sufficiently strong, probably at a given frequency, can dominate the detonation propagation instead of the self-induced, because there could be like a competition of the two.
Yes.
So actually,
So actually, let me just paste. I'm going to put it in the chat here. The DOI for this is a shameless plug, but this is when you asked that question in your talk, this is a combustion symposium paper that is just in press. So my name is on it. It's the work of a student. So I hate doing this. My name is on it, but it's the work of a student of Professor Ring with us at Concordia. But that student, Mira Kim, was actually specifically looking at different different perturbation frequency and amplitude. These are numerical experiments here, not analytical results, but different perturbation frequencies and amplitudes, and then she showed that you can get the regularization of a intrinsically unstable detonation. So in the high activation energy,
great!
You actually see. So this is not an analytical solution, but it's a numerical experiment. So we know numerically that for the 1D case, this is possible. So just if you've not seen it come out, I thought I would put it out. So there's
thank you.
But again, this is a numerical experiment, so it includes the post the numerical domain extends beyond the sonic locus in this particular case. And so it's a good question whether do you have to consider both the detonation structure itself and the downstream flow.
Okay, so.
But that's so that's the anyway. That was my question / comment. Was it? So I do understand how you set up your stability problem in this case.
Yes, and actually we are thinking about trying to include in the model the effect of the activation energy, which is the parameter that I didn't show because I have not included. So thinking about that, what we think is that by looking into the conservation equations, the one that is for sure not true is the tangential velocity conservation. If I have velocity here measured at the detonation wave, the conservation of tangential velocity is true across the shock, but it won't be like that in the flow downstream. So we want to include, we want to find, I mean, we are working on that. This is, I mean, I'm super open for suggestion, or you can say that this is not going to go anywhere. But I mean, the thing is that with modeling that, I have the sense that we have to be careful because, I mean, reactive Euler equations, as they are not super complicated equations. You don't have a complicated transfer property or whatever. So I'm afraid of trying to use in a theoretical model that at the end of the day is including like fitting parameters that is making the problem even less harder to be written than the Euler reactive equations. Mm-hmm. What we have thought that can be done is to include the information of the activation energy, which is actually the form of the shape downstream, mm-hmm. but trying to include it in an integral form. I mean, not trying to solve the inner structure, because this is you have to do it numerically, as far as I know. But trying to use this information as an integral parameter that's telling me, depending on this condition, I'm the tangential velocity would be higher than the other. There would be like a flux of energy, momentum, and mass. And depending on this shape, this will modify the properties downstream. So what I want to do is to use that information in a 1D model and try to include this in the conservation equation. For instance, what I told that velocity downstream is something like that. Mm-hmm. But this is for the shock. This is not true for the detonation. So how can we use that to include this information of the inner structure into trying to pose a problem that can be solved analytically from the burn gas dynamics, but includes the most important information of the inner structure? I mean, linear, it won't give you the cellular patterns because this is by definition, they are not linear, but at least it can affect the transfer functions of depending the perturbation upstream, I get that perturbation downstream, and probably it can get you the stability limits. I'm not sure, very likely they are not. You have to go inside, but if so, you can get an analytical dispersion relationship for the detonation front, including information about the inner structure. That would be the main goal with that approximation.
Yeah, I wish we could. Hopefully we can get Mark's comments on your work as well. Just one last, because the second major assumption that I saw you made in setting up the stability problem is that you assume the infinite Mach number limit. So you're effectively assuming a zero activation. Again, correct me if I'm wrong. So it's the zero activation energy limit with an infinite heat release, basically, is what you're assuming, right? So by using the infinite Mach number assumption to get rid of the pressure perturbation, you got rid of the transfer of the. There was one slide where you showed you neglected.
Oh yeah. Sorry,
the propagation.
It was my fault for not writing that one.
Yeah, right there. Yeah, that's right. So
this is the perturbation upstream. This is like the strong assumption. This is the same thing that you do when you solve the Feldovitz-Taylor explosion problem, where you don't care about the pressure upstream because pressure downstream is much higher. But I'm not neglecting pressure downstream. Maybe I went too fast.
No, but you're. Hold on. What are you neglecting here? Then I missed this. Then upstream perturbation.
Yes, what I wanted to show here is that you think about a general perturbation problem upstream. You have a mixing in non-equilibrium. Density perturbations coexist with velocity, pressure, and other perturbations in the flow.
Right.
But the thing is that if you are looking into sufficiently strong shocks, and this is something applicable to detonations, you can forget about velocity and pressure, because in the strong shock limit, pressure and velocity upstream is negligible because the velocity of the detonation, let's call it T, is much higher than the velocity, and also the pressure, the dynamical pressure is much higher than pressure upstream. So the same thing that you do for the base flow to calculate, for instance, the Dobitz-Taylor problem, you can do for the perturbation analysis. What matters in the perturbation analysis when you look at detonations is the density perturbations upstream. Is the only one that in the Strong-Shock limit remains finite.
In the Strong-Shock limit.
Yes, but I'm not saying that it has to be overdriven. It applies also for a time and Huete. Is that
exactly
it is
right? Exactly. Which is saying that the heat release is large.
Yeah, in that case is yes.
Since the
yes.
shock speed is
sufficiently high. Yes.
Yeah. So it's the limit of zero activation energy, infinite heat release. Is the sort of the transfer function that you're considering the detonation to be, or am I?
Okay. I don't know, Mate. Probably I don't know. I have to think.
I'm trying to think in terms that I normally. Okay, I'm going to stop making comments now, but I'll hopefully we can get Mark's microphone on and see what his comment was.
Thank you for the comments.
Thanks.
Thank you, Charles, for your question and comments. Yeah, I told Professor Mark Short to just write down his question in chat, and if his microphone is not working, but I didn't see something from him yet. Is there any other questions from the audience or comments? If you do, please unmute yourself and just directly ask César. If not, I have another question, or like just about the implication of this. You show that in certain conditions that you can show that this perturbation of the transverse wave instability can be exactly equilibrated at certain conditions, right? Like what exactly that implication of that is? Does it mean that you can somehow control the fluctuations upstream so that you can suppress the instability?
Yes, that's I mean, the thing is that in linear theory, it does. I mean, in the real problem, including the effect of the induction length and the activation energy, that there is a self-induced evolution of the detonation that has nothing to do with the upstream flow.
Right.
My question was, is there any way to modify the upstream to force the detonation to do what the upstream flow tells it to do instead of the self-induced, the self-mode, right? Self-oscillation mode. That's what the question that I opened, that Matei just said, that for one-dimensional, they can control the detonation, what the upstream flow can tell it to do. But I mean, I'm so looking forward to look at this paper, because there was a question that I didn't work on it, but I mean, it would be great to look at it.
Okay. Yeah, I think that is interesting, because what I see is like if you make these perturbations very non-linear, like you just you're totally moving out of this intrinsic nature of detonation in the homogeneous pre-mixed mixture, then like you definitely like suppress any of this like cellular structure or intrinsic instabilities associated with the gas phase detonation. But that has somehow in this simple way that I used to discretize the medium, is just like to make the energy concentrated to like a very highly discrete energy sources. Yeah, but I don't know, like if there is a way somehow like you know, like the medium is somehow still continuous, like a sinusoidal or somehow like you know, continuous distribution, and also go to this limit that as you said, that the inhomogeneities in the mixture dominates, totally renders the detonation structure, and in that case then the intrinsic instabilities are totally suppressed, right? So yeah, that's an interesting question. I don't, yeah, for me, I don't have a quick answer on like how to have such a continuous medium to do that. I don't know. because the one problem is that if you make it continuous and you introduce this strong enough inhomogeneities, then you may leave some gap that somehow like inert gap or not very reactive gap, right? So that can maybe, I don't know, this is maybe quench the detonation.
Yes.
Or just it's interesting to maybe think about some numerical experiment that we can do, and also you can perform an analysis on that. Yeah, I think there is a.
I was going to. Oh, sorry. Am I taking someone?
Yeah, I think
no.
No,
I was just going to mention.
Sorry. Go ahead. Yeah.
But I mean, it's quite interesting. But in the work you did for the slab, the slab detonations or the slab medium for detonations, there's by collecting, even in the small gamma limit, by collecting the energy into layers, you're still introducing basically infinite slopes, right? Every time you have one of these layers, you're introducing a delta function inside. Like there's a big kick to the detonation. So I don't know that. Maybe I'm trying to see if this is what you were just saying now, but so I'm sort of rephrasing. But you're maybe there's a way to redo all of the work you did, as another student's job there. But to redo it, but then reformulate your discretization of your inhomogeneity into a continuously. You see what I mean, right? Like a continuous change instead of introducing these delta functions periodically, because
By the way, I got a private message from Professor Short. He said like his microphone is not working, but his question is quite involved, so he will follow up with César later. Yeah, probably if he can share this with the entire audience, it will be even better. I think like we're gonna upload, because eventually we will upload the video to YouTube, and like maybe Professor Short can share his question in the discussion board of YouTube. If that's
I can send the presentation PDF format, so maybe he can look easier and faster to the point he wanted to talk about.
Yeah.